Most of Saudi Arabia receives less than 100 millimeters of rain annually, about the height of a coffee cup. But every day, millions of people here drink water that began as seawater hundreds of kilometers away. The real achievement is not only the desalination plant, it is the steel river crossing the desert, a system of pipes, pumps, valves, tanks, and filters that keeps water moving. From seawater intake to the household tap, every step of that journey will be unfolded here.
A modern skyline rises from desert terrain where water remains scarce. Riyadh, Saudi Arabia, demonstrates a challenge: sustaining expanding cities when dependable natural freshwater supplies remain limited. As cities expand, water demand grows with them. Saudi Arabia is investing in tourism, infrastructure, services, and new destinations designed to attract millions of visitors. Hotels, transportation systems, healthcare facilities, and commercial districts all require reliable fresh water every day. Economic growth can be funded by energy resources, but drinking water, sanitation, cooling, and daily urban operations require a secure physical supply. That creates the central problem of this project. Where can a desert nation find a dependable source large enough to support modern life? Natural water supplies are not always predictable. Population growth, industrial activity, and expanding urban areas place constant pressure on available resources. A city cannot pause hospitals, homes, factories, or public services because rainfall falls short in a particular season. One solution is to stop depending entirely on weather and turn to the sea. Seawater offers an enormous resource that is available every day, regardless of annual rainfall patterns. Instead of waiting for nature to provide fresh water at the right time and in the right quantity, desalination plants produce it through a controlled industrial process. Large facilities are designed to transform seawater into drinking water while supporting long-term demand. Intake systems draw water from offshore locations, treatment equipment removes unwanted material, and transmission pipelines connect production sites to storage and distribution networks. Reliability becomes something engineered rather than something left entirely to natural conditions. But choosing the sea only solves the first part of the problem. The water available in the ocean is the wrong kind of water for people and cities. Seawater appears unlimited, yet it contains salt, suspended particles, organic matter, microorganisms, and other impurities. A single liter of seawater can contain tens of grams of dissolved salts that must be separated before the water becomes usable. Before it can enter a drinking water network, it must pass through multiple treatment stages designed to protect both people and infrastructure. The process begins offshore. Intake pipes extend into the sea to collect water from cleaner locations away from shoreline disturbance. Screens help prevent larger debris and marine organisms from entering the system while maintaining conditions that reduce environmental impacts. After arriving at the plant, seawater passes through initial screening and pre-treatment stages. Sand, fine particles, seaweed fragments, and other contaminants are removed before the water reaches the most critical equipment. This preparation stage protects downstream systems and improves overall treatment performance. Without effective pre-treatment, membrane systems can experience faster fouling, reduced efficiency, and higher operating costs. The next step is reverse osmosis. Powerful pumps force water through specialized membranes containing microscopic openings. These membranes allow water molecules to pass while rejecting dissolved salts, bacteria, viruses, and many other unwanted substances. Reverse osmosis has become one of the most widely used desalination technologies because it can consistently produce high-quality fresh water from seawater. The resulting water is extremely pure. Minerals are therefore added back in controlled amounts, so the water is suitable for distribution and consumption. At the same time, concentrated brine is managed through dedicated discharge systems designed to promote rapid dilution after release. What emerges from the plant is not simply cleaner water. It is a manufactured resource produced through a sequence of engineered steps: intake, screening, pre-treatment, reverse osmosis, remineralization, pumping, storage, and distribution. The ocean supplies the raw material, but technology transforms it into water suitable for homes, hospitals, industries, and expanding cities. Even after fresh water is produced, another challenge remains: moving it across long distances of desert terrain. Countries without major natural rivers can create an industrial river instead. Long steel pipelines, pumping stations, storage facilities, large valves, monitoring systems, and control rooms work together to transport water continuously across harsh landscapes. The river is largely invisible from above, yet it delivers the reliability modern cities require every day. Before a single drop of desalinated water can move toward a city, the steel that will carry it has to be manufactured. And a pipe this large cannot simply be rolled and trusted. It has to be shaped like a machine part. A flat steel plate arrives at the production line by magnetic overhead crane, positioned precisely on the roller conveyor. An edge milling machine trims both long edges to uniform dimensions, because even a fraction of a millimeter of mismatch will produce a weak seam later. A pre-bender curls the outermost edges first, preparing them for the main forming stage. The plate then advances step by step into the JCO press bending machine. A massive hydraulic press descends onto the plate at measured intervals, bending it progressively into a J shape, then a C shape, and finally closing it into a full O, a cylindrical shell ready for welding. Each stroke is positioned by electronic control, because the finished pipe has to meet strict diameter and roundness tolerances across its entire length. A transfer car moves the formed shell to the welding stations. A tack welder locks the open seam in place. An inside welding machine runs a continuous bead along the interior of the seam, building the structural bond from within. A back bead cutter trims the excess weld material flush with the surface. An outside welding machine then seals the exterior seam. Once welded, the pipe moves through a four-way expander that presses the cross-section into final calibration, correcting any ovality left by the forming process. An end-facing machine chamfers both open ends to prepare them for field welding later. A washing device cleans residue from inside and outside surfaces. An X-ray testing machine scans the full length of the seam under radiation shielding, verifying internal integrity before the pipe is cleared. A varnish coating machine applies an initial protective layer. The finished pipes are conveyed to the outgoing area and loaded onto flatbed trucks for delivery to the coating plant or directly to the construction corridor. A spiral mill can produce them continuously, and the seam it creates wraps around the pipe like a thread on a bolt. A steel strip passes through an edge milling unit and is ultrasonically inspected before entering the forming section. The strip is holistically wound into a tube shape, and 5 electronically controlled welding heads apply internal and external beads simultaneously. Strip gap alignment is precision controlled to ensure full weld integrity. After cutting, each pipe undergoes ultrasonic testing, hydrostatic pressure testing, and full-length radiographic inspection to confirm a weld factor of 1. A pipe without a valve is just an open tube. The moment engineers need to isolate a section, regulate pressure, or shut down flow in an emergency, the valve is what stands between control and failure. A valve automation facility shows the full assembly sequence. Engineers begin with a contract review and production plan. Valve adapters and control layouts are designed in 3D CAD software. Materials are ordered, checked against the bill of materials, and moved to the shop floor. Technicians bend tubing, build control panels with pressure gauges and signal transmitters, and mount the completed panel onto the valve body. A large actuator is craned into position on top of the valve, bolted down, and mechanically aligned. Functional testing follows. Pneumatic pressure is ramped to verify response. Electrical signal feedback is confirmed, and a manual override hand wheel is checked to ensure the valve can still open and close safely if power is lost. Valves control where the water goes. Pumps are what push it there. A dedicated stainless steel pump factory produces vertical multi-stage units designed using CAD, CAM, and CA software. Press tools and dies are manufactured in-house. Motor lamination and winding wire are produced internally to control efficiency at the source. Accelerated life testing confirms long-term durability. These pumps are rated for reverse osmosis water purification plants and hydropneumatic pressure systems built in multiple stainless steel grades suitable for drinking water service. Steel is strong enough to carry pressurized water across a desert. But without protection, it can corrode when exposed to moisture, salts, and electrical currents. To prevent this, raw steel pipes pass through a specialized coating process before installation. The pipes first enter a grit blasting chamber that removes rust and cleans the surface. Technicians then inspect the surface profile to ensure it meets coating requirements. After inspection, the pipes move through a heating zone where burners raise the steel temperature. A primer layer is applied, followed by polyethylene coating that melts onto the heated steel and forms a durable protective barrier. The coated pipe is rapidly cooled with water to secure the layers in place, while the interior receives its own protective lining. Quality control follows every stage. Digital gauges measure coating thickness. Holiday detectors search for pinholes or uncovered areas. And adhesion tests verify the bond between steel and coating. Each completed pipe is marked with a tracking code before being loaded for transport. Inside the factory, every step is carefully monitored. The goal is simple. Ensure the pipeline can withstand decades of service once it reaches the harsh desert environment. Inside the factory, everything is still under control. The real challenge begins when those pipes arrive at a construction corridor, cutting through open sand, rock, and 50-degree heat. Before the first trench is dug, engineers have already made one of the most important decisions: where the steel river is allowed to exist. A transmission pipeline cannot simply follow the shortest line on a map. Designers evaluate terrain, soil behavior, maintenance access, crossings, existing utilities, erosion exposure, and locations where unstable ground may create long-term risks. An unsuitable route can introduce unnecessary stress concentrations long before water enters the system. After the preferred corridor is selected, planning expands beyond the pipe itself. Construction teams require space for transport, storage, excavation machinery, welding spreads, coating crews, inspection vehicles, and constant material deliveries. On major projects, a working corridor roughly 40 meters wide may be prepared so several activities can advance simultaneously. Logistics become a major undertaking. Large quantities of steel pipe must arrive in sequence, be unloaded, staged, tracked, and moved to the correct locations at the proper time. Longer sections reduce field joints, but demand specialized handling. By then, much of the project's success has already been determined through route selection, access preparation, and coordination across the entire corridor. With the route chosen, the desert must be prepared to accept an industrial river. A large pipeline requires much more than a narrow trench. The first visible step is creating a construction corridor wide enough for trucks, excavators, pipe carriers, side booms, welding crews, coating teams, inspectors, and support vehicles. A cleared working strip also allows materials to move continuously along the route without disrupting other operations. Pipe sections are transported to the corridor and laid out in sequence beside the future trench. Equipment then adjusts individual sections to match changes in direction, elevation, and terrain. Even small deviations matter because a transmission pipeline may extend for hundreds of kilometers. Construction progresses as a coordinated chain rather than isolated tasks. Material staging areas support the flow of steel, equipment, fuel, spare parts, and personnel. If one activity falls behind, the delay can spread through the rest of the operation. Careful scheduling keeps excavation, pipe placement, inspection, and restoration advancing together. The corridor also serves as a controlled workspace where crews can manage safety, access, and quality checks. Every vehicle movement, delivery sequence, and work zone contributes to overall productivity. What appears from the air as a long, cleared strip across open land is actually a temporary industrial system designed to keep construction moving efficiently from one end of the route to the other. Then, the route begins to reveal the obstacles hidden within the landscape. Pipeline construction rarely crosses uniform ground. Slopes, difficult access zones, changing elevations, and challenging terrain require constant adaptation. Progress depends on preparing the route carefully before major installation activities can move forward safely. The pipeline only becomes one pipeline at the moment two ends are joined. Until then, it is just a yard full of separate steel sections waiting for a perfect line. The Ojinaga to El Encino route runs 222 kilometers of 42-inch pipe across mountain ridges and desert in Chihuahua. 80 people and dozens of machines move down the corridor in a continuous formation. Surveyors set the line. Excavators open the trench. Welding crews close the gap. Inspectors check what was just made. Coaters seal the new joint. Side booms hold the string in the air until the moment it goes down. The first task at every joint is geometry. Two pipe ends, each weighing several tons, must sit on the exact same center line before any welder strikes an arc. A small offset between ends does not look like much from outside. Inside the steel, it shifts the load path of the future weld. When the line is pressurized for decades and pressure cycles up and down with demand, that offset becomes the place where stress concentrates first. Internal lineup clamps go into the pipe, expand against the inner wall from both sides of the joint, and hold the two ends concentric while the root pass is laid. Field welding looks nothing like a factory floor. The shop comes to the pipe, one joint at a time. Automatic welding tractors are staged in a line along the strung-out pipe sections. A crawler excavator and a yellow pipe layer lift one pipe end into position. A safety engineer stands directly under the suspended section and signals the lift with hand gestures. The gap between the two ends must be set to the design tolerance, measured in millimeters. When the gap is right, the internal lineup clamp is pushed inside the pipe and expanded against the inner wall. The clamp holds the circular shape of the steel from the inside while the first weld pass is laid down outside. A protective shelter is moved over the joint to block wind and dust. The automatic welding head rides on a track wrapped around the pipe, traveling 360 degrees around the circumference, at a programmed speed and laying down weld metal in controlled layers, pass after pass, until the joint is complete. Once the trench is backfilled, no one will see the weld again for the life of the pipeline. So every weld is checked while it is still in the open air. Non-destructive examination follows the welding crew at the same pace. The first method is real-time radiography. A radiographic crawler is sent through the inside of the pipe to the position of each new joint. From the outside, a corresponding detector captures the image. The internal structure of the weld appears on a screen within seconds. Inspectors look for cracks, lack of fusion, porosity, and inclusions that cannot be seen from the surface. The second method is automated ultrasonic testing. A motorized scanner ring wraps around the outside of the pipe at the joint and rotates a full 360 degrees, sending ultrasonic pulses through the weld material. The system measures the echo from any internal flaw and records its size and depth with millimeter accuracy. A coating only sticks to steel that is truly clean. Cleanliness on a pipeline is not visual. It is measured in surface profile, microns deep. The principle is shown most clearly in a plant environment, on 16-inch steel pipe in 12-meter lengths. An internal blasting head is mounted on an extending mechanical arm and pushed into the bore of the pipe. The head is centered on the pipe axis, so the abrasive stream hits the inner wall evenly. High-pressure air drives steel grit against the surface. The blasting head traverses the full length of the pipe and strips the entire internal surface down to bare metal. After the pass, a camera is sent inside to inspect the result. Dry compressed air is then blown through the bore to remove all residual dust and grit. The before and after contrast is direct. Rust-red oxidized steel becomes uniform silver-gray metal with a controlled surface profile. The same blasting principle, scaled down and made portable, is what coating crews use on every field joint along the route. The body of every pipe section was coated in a factory. The field joints were not. Every weld is a gap in the protection, and every gap must be closed before the pipe goes underground. At each joint on an overland route, the coating system runs through its cycle. The oxidized weld area is sandblasted to bare metal. An induction coil is placed around the joint and preheats the steel to coating temperature. A coating ring is lowered into position around the pipe. The nozzles are purged. The ring rotates around the joint and sprays a multi-component liquid coating evenly across the surface. The full cycle takes under 40 seconds. Once every joint has been coated and sealed, and tens of kilometers of pipeline have been lowered into the trench, the next section of the route extends offshore, where the seabed is no longer a flat and predictable surface. The path from open sea to the first pump is already an engineering project on its own. On the northern tip of the Nile Delta, facing the Mediterranean, a desalination plant produces 80,000 cubic meters of drinking water per day. 2 HDPE intake pipelines run 1.25 kilometers out from shore. Combined suction capacity reaches 211,000 cubic meters per day. The intake towers at the outer end sit at designed levels under the seabed, anchored against currents, waves, and shifting sand. Placing those towers required waiting for a narrow window of acceptable weather. The coast along the delta is exposed to the open Mediterranean. Swells, wind shifts, and underwater visibility all have to line up before a heavy concrete structure can be lowered to its final position on the bottom. Once set, the towers pull seawater by gravity through the 2 long pipes to a wet well onshore, 10 meters below sea level. A separate outfall pipeline returns concentrated brine back to open sea at a discharge capacity of 131,000 cubic liters per day. The intake and the outfall are placed far enough apart that rejected salt does not loop back into the intake feed. Below the surface, the intake towers are already part of the reef. Marine life clusters around the concrete. Sea squirts, sponges, blue mussels, stinging hydroids, and seahorses attach themselves to the structure and to the brine diffuser outlets nearby. The intake draws seawater at a speed slow enough that fish swim away from the opening without effort. This velocity control is deliberate. A faster draw would pull small organisms and debris into the pipeline, increasing the biological load on filters downstream. A slower draw lets the ocean sort itself. The marine colonies growing on the diffuser confirm that the diluted brine return does not sterilize the surrounding water. The seawater has arrived on shore. Now, the plant has to strip everything the ocean carried in with it. A raw water intake station shows the full screening sequence. At the channel entrance, a trash rack, vertical steel bars spaced to pass water, blocks floating debris like branches and drifting waste. Behind it, a sluice gate controls flow into each bay. Engineers can shut one bay for maintenance while the others keep running. Past the gate, a traveling band screen handles finer material. The screen is a continuous mesh belt rotating through the water column. As the belt rises above the waterline, high-pressure jets blast captured debris off the mesh into a collection trough. The screen never stops moving, so the surface stays clean. Below the screen chamber, large vertical pumps draw the cleaned water into pressurized mains heading toward the treatment plant. What the screens miss is invisible, but still dangerous. Ultrafiltration membranes are hollow straws with pores 700 times smaller than a human hair. Seawater is pumped through them. Viruses and bacteria cannot pass. The water leaving this stage looks clear, but every gram of dissolved salt remains. Even after screening and ultrafiltration, Seawater still contains fine particles. Dual media filters use layers of anthracite and sand to remove them before reverse osmosis. When clogged, the filters are backwashed with air and water, then return to service.
By this point, the seawater looks clean. Chemically, every liter still carries around 35 grams of dissolved salt, and removing that requires an entirely different kind of force. Salt is not floating debris. It is dissolved at the level of individual ions, and no mesh in the world is fine enough to catch it. To remove salt from water, the entire approach has to change. The barrier stops being a filter and becomes a membrane that lets water molecules pass while holding ions back. On the Gulf of Oman, the Fujairah 2 reverse osmosis plant produces 136 million liters of drinking water per day, making it one of the largest of its kind in the world. The full process runs in sequence: seawater intake with chlorination, dissolved air flotation, gravity filtration, cartridge filtration, two-pass reverse osmosis, then blending and remineralization. Screened seawater is pumped by 4 turbine pumps into the pre-treatment line. The first step is coagulation and flocculation. Chemicals are dosed in, then mixed gently to form small flocks that bind suspended particles together. The flocculated water then enters 16 dissolved air flotation units. Microscopic air bubbles are generated and rise through the water. The bubbles attach to the flocks and lift them to the surface, where they form a brown scum layer that is skimmed off periodically as waste. These DAF units exist specifically to block red and green algae and the organisms responsible for harmful algal blooms and red tides. The pre-treated water then passes through 10 gravity filters. Each filter contains a top layer of volcanic pumice over a deeper layer of quartzite sand. After 40 to 60 hours of service, each filter becomes loaded with trapped material and is backwashed one at a time. All waste streams and scum are sent to 2 centrifuges that dewater the sludge into a dry cake for safe disposal. After gravity filtration, the water is pumped by 10 booster pumps through 16 cartridge filter vessels. Anything larger than 10 microns is captured here. This polishing step is the last physical defense before the membranes. The polished feed water then enters the 2-pass reverse osmosis stage. The first pass uses 10 racks, each fed by a dedicated high-pressure pump, driving the seawater into the membranes at 65 bars. Inside each pressure vessel, water molecules cross the membrane while dissolved salts are rejected. The output splits into 2 streams: permeate, which is fresh water, and brine, which carries the rejected salt at higher concentration. Anti-scaling chemicals are dosed continuously to prevent mineral deposits from building up on the membrane surface. Periodic cleaning with caustic soda and citric acid keeps the membranes operating at design output. The brine leaves the membranes still carrying around 60 bars of pressure. That pressure is recovered with Pelton turbines that drive the high-pressure pump motors directly, reducing electrical demand from the grid. The first pass permeate then enters a second pass of 2 racks, where unwanted boron is removed to meet drinking water regulations. The final permeate is blended with distillate from the thermal side of the hybrid plant, remineralized, disinfected, and stored in 4 large tanks before distribution. The membrane is only as useful as the pressure pushing water against it. Large vertical pumps stand in line along massive distribution piping. Stable pressure keeps the filtration process consistent. Pressure gauges on the local control panel read directly in bar, and dedicated motors drive each unit at full, continuous duty for the urban water supply. Across desalination plants worldwide, the high-pressure section uses several specific pump types. Dynamic sealed pumps with hydraulically balanced impellers, split casing pumps with improved hydraulics, and axial flow pumps for high-volume duty. At the upper end of the scale sits the vertical column turbine pump. A single VCT 78 CBXM unit, measured and verified at the factory before shipment, feeds part of the expansion at the largest desalination plant in Morocco, supplying water for 1.5 million people. A reverse osmosis rack is not a single machine. It is a series of pressure vessels arranged in parallel, and each vessel contains multiple spiral-wound membrane elements installed by hand. Before loading begins, technicians gather the required equipment: safety shoes, rubber gloves, food-grade lubricant such as glycerin or Molykote 111, clean rags, a ratchet wrench, membrane elements, interconnectors, permeate blind adapters, end cap assemblies, thrust cones, and a feed spacer assembly. Work starts by opening the pressure vessel at the permeate manifold. Victolic couplings connecting the permeate port to the PVC manifold are removed, followed by the PVC unions. Once the manifold is taken away, retaining rings at both ends are removed and the end caps are extracted. The vessel interior is then flushed with water and wiped clean to remove any debris. Lubricant is applied to the inner wall on the brine side and to the head seal. A thrust cone is mounted on the brine side end cap with its wide face toward the lead membrane element. The permeate through adapter is fitted to the inner side of the permeate port, and the end cap is secured with retaining rings. Membrane loading begins from the feed side. Each element carries a directional arrow, and the V-ring brine seal must face the tail end. The first element is pushed most of the way into the vessel. Lubricant is applied to the V-ring and the O-rings on the inner connector, which is inserted halfway into the permeate tube. The next element is aligned and slid onto the interconnector without placing weight on it. The same sequence is repeated until all elements are installed. The final membrane receives a blind adapter on its permeate tube and is held by the feed spacer assembly. The feed side end cap is then installed and locked in place with its retaining ring, completing the vessel assembly. Energy is the largest single operating cost in seawater desalination. The plant that wastes the pressure in its brine stream pays for it every hour, every day, for decades. A PX pressure exchanger captures that pressure directly. The device contains a single moving part, a ceramic rotor housed inside a sleeve sealed by two end covers. High-pressure brine from the RO membranes enters one side. Low-pressure seawater enters the other and fills the rotor at the same moment. Inside the rotor, hydraulic pressure transfers directly from the brine to the seawater. The now pressurized seawater leaves the device and joins the main feed stream from the high-pressure pump. The depleted brine exits at low pressure. The rotor spins on a water film, requiring no external lubrication, at speeds up to 1,200 revolutions per minute. A single device runs at 98% efficiency. Combined in parallel, PX units cut seawater RO operating energy by around 60%. Water leaving the RO membranes is almost pure H2O. Pure enough that it is corrosive to pipes and flat in taste. Lime is added to correct pH and protect the network. Chlorine is dosed for disinfection. Before a single liter leaves the plant for the distribution network, it has to pass one last check that has nothing to do with salt. A water sample is collected and diluted. The diluted sample is filtered through a membrane under vacuum. The membrane is transferred onto an absorbent pad in a petri dish containing nutrient broth. The dish is incubated at 35 degrees Celsius for 24 hours. After incubation, red and blue colonies are counted for total coliforms. Only the dark blue colonies are counted for E. coli. To be classified as potable, the sample must show 0 coliform bacteria. The work is performed under aseptic conditions to prevent contamination of the sample during handling. Testing for coliforms is the standard indicator method, cheaper and faster than testing for every possible pathogen individually. But once the water is drinkable, its journey is far from over. It must leave the treatment plant and travel deep into the desert. Moving water on this scale requires enormous energy. At Lake Mead, the low lake level pumping station uses 34 submersible pumps installed 500 feet below ground. Each unit can move up to 30 million gallons daily while lifting water hundreds of feet vertically. Together, the station delivers as much as 900 million gallons daily to 2 downstream treatment plants. Before entering service, every pump undergoes a 2-hour performance test to verify that it meets its design specifications. The facility is capable of supplying water to more than 2 million people, making it one of the largest high-capacity pumping systems ever built. A pipeline delivers water at a steady rate. A city consumes it in spikes. Something has to absorb the gap. That role belongs to large storage reservoirs and ground tanks placed along the network. The post-tensioned concrete tank built for Kearns Improvement District in Utah holds 5 million gallons of culinary water. A single ring of pre-stressed concrete with vertical and circumferential tendons tightened after the wall is cast. The wall is held in compression at all times so it cannot crack under hydrostatic load from the water inside. Construction begins with a deep ring foundation. Wall panels are cast in place around the perimeter. Steel tendons are routed through ducts inside the wall, then tensioned against the concrete to lock the structure in compression. A flat or domed roof is poured on top. Inlet and outlet piping, overflow lines, drainage, level instrumentation, and disinfection contact volume are all designed into the geometry before the first pour. The full project took more than a year and a half to complete. A buried pipeline cannot be watched with eyes. It has to be watched with data, second by second, across hundreds of kilometers. Supervisory control and data acquisition pulls real-time readings from pumps, valves, pressure points, flow meters, and tank levels across the whole network. Operators see the system from one room. Problems are flagged before they escalate. A pipeline is finished the day it is buried. Then it starts aging, and the work to keep it alive begins. A utility may operate a network of nearly 5,000 miles of pipeline, ranging from 3/4 inch to 96-inch diameter, with pipes from yesterday up to over 70 years old. Large diameter mains are monitored 24/7. Steel pipe rusts. Buried in soil with moisture and oxygen, it rusts faster. Cathodic protection moves the corrosion off the pipe onto something else, intentionally. Magnesium anodes are buried near transmission pipelines 2 feet in diameter and larger. Each 48-pound block is wired to the pipe. The magnesium corrodes preferentially while the steel stays intact. A single installation extends pipeline life by up to 25 years, with hundreds of test stations added each year. Desalination does not make salt disappear. It separates clean water out and leaves behind a saltier stream, brine, that has to go somewhere. The Tampa Bay plant produces up to 25 million gallons of drinking water per day, supplying around 10% of regional demand. RO uses pressure up to 1,000 psi to push seawater through membranes that block anything larger than 0.001 micron. The RO process leaves behind about 19 million gallons per day of concentrate at roughly twice the original salinity. That concentrate is mixed with the adjacent power station's cooling water, providing 24 to 70 times dilution in the pipe before discharge. Water quality monitoring shows no measurable salinity change in Tampa Bay tied to plant output. The future of desalinated water is not bigger plants. It is smarter plants, using less energy, integrating renewables, and treating brine as a recoverable resource rather than waste. Wind turbines and solar PV are now integrated into desalination sites. Research is underway to turn brine into recoverable mineral products. Energy is the largest operating cost of desalination. The most direct way to cut it is to take energy straight from the sun. Solar-powered desalination uses photovoltaic panels to run the high-pressure RO pumps directly. Energy recovery technology captures residual pressure from the reject stream and reuses it, cutting required input energy by 75%, meaning 4 times fewer solar panels. A minimal battery bank handles cloud cover and short interruptions in sunlight. Producing desalinated water is expensive. Using it once and throwing it away makes that cost permanent. The future of any large water system depends on what happens after the tap. Wastewater enters a treatment plant through the sewer network. The first stage is step screens that remove large solids, anything that should never have entered the system in the first place. This early separation protects downstream equipment from damage and blockages. Captured material is washed and sent to landfill. What passes through the screens reaches the grit chamber, where water velocity is slowed and air is bubbled through the flow. Heavier solids like dirt, sand, and small rocks settle to the bottom. The combined waste from screens and grit is roughly 1 ton per week at a mid-sized plant. The water then flows into primary clarifiers, large circular basins where gravity does the work. Water enters at the center and moves slowly outward over 5 to 6 hours. Dense sludge settles to the bottom. Sweeping arms collect the sludge and skim floating debris from the surface. Around 90 to 95% of settleable solids and 40 to 60% of suspended solids are removed by this stage. From the clarifiers, screw pumps lift the water into the next process. Most of it flows to aeration basins, where mixing wheels stir the water and pump air through it. Beneficial bacteria living in the basin feed on the dissolved organic load. Billions of microorganisms are working continuously inside every aeration basin. This is an aerobic biological process, a natural cycle harnessed at industrial scale. A portion of the flow goes through a trickling filter, where water is sprinkled over plastic media coated in bacteria, removing ammonia and other contaminants. After biological treatment, the water enters secondary clarifiers. Activated sludge settles, and a large fraction of it is returned to the aeration basins to keep the bacterial population alive. Excess sludge is sent to digesters. The cleaned water then flows into the chlorine contact basin. Chlorine is mixed into the stream from a holding tank, and the long contact channel gives the disinfectant time to act before the water is discharged. Disinfection is the final barrier before the water leaves the facility. Total time inside the plant is around 18 to 24 hours per gallon. The sludge takes a separate path, at least 15 days in anaerobic digesters, then through a belt press that raises solids content from 4% to nearly 18%. The dried material leaves the plant as fertilizer for farms or as landfill cake. What Saudi Arabia built is not just a desalination industry. It is a national-scale water machine. The sea provides the raw material. Membranes remove the salt. Pumps create the pressure. Steel pipelines carry the flow across vast stretches of desert. Storage tanks protect the reserve, while control rooms monitor every stage of the journey. Together, these systems replace the role that natural rivers play in other parts of the world. In a landscape where fresh water is scarce, engineering created an invisible river from scratch and keeps it moving every day. What do you think is the hardest part of this system? Removing the salt? Building the desert pipeline? Or keeping the whole network running every day? Leave your thoughts in the comments and follow along for more behind-the-scenes engineering stories.